Welcome to lecture 3.5, Derivatives of Logarithmic and Exponential Functions, Part 1, Limits and Definitions. Logarithmic and exponential functions and inverse relationships. Consider the functions f of x is equal to 2 raised to x and g of x is equal to the logarithm of x to the base 2. F of x is an exponential function whose output value is when a certain numerical base is raised to a power. For example, we have here the resulting equation would be 2 raised to 3 is equal to 8. It means that 2 will be multiplied to itself 3 times. That is the use of the exponential function. So it let us compute the value, the output value, given a specific input value. The input value x tells us how many number will be multiplied to itself. This is the graph of the exponential function 2 raised to x. The domain is the set of real numbers and the range is the open interval from 0 to positive infinity. It is asymptotic to the x-axis. Next, we have the logarithmic function g of x. Logarithmic function whose output value is the logarithm or the exponent. The certain numerical base must be raised into to obtain a certain quantity. The logarithm of 8 to the base 2 is equal to 3. So take note that this is the what we call exponential form, and then this is what we call the logarithmic form. They are both equivalent to each other. 2 raised to 3 is equal to 8 is equivalent to logarithm of 8 to the base 2 is equal to 3. The domain of the logarithmic function is the open interval from 0 to positive infinity, and the range is the set of real numbers. It is asymptotic to the y-axis. Suppose that f of x is defined by a positive real number that is not equal to 1 multiplied to itself x times. Then symbolically, f of x is equal to a raised to x. This is what we call the exponential function, where a is the what we call base, and a is a positive real number, not equal to 1. And then x is what we call the exponent. On the right, you will see the graph of y is equal to quantity 1/2 raised to x, and then the color blue, y is equal to 2 raised to x. So they are mirror images to each other with respect to the y-axis. Here is a definition of the logarithmic function. It is the inverse of exponential functions, and it returns the exponent needed for a certain numerical base to be multiplied to itself to get another quantity. We have f of x is equal to the logarithm of x to the base a, where a is the base and a is a positive real number not equal to positive 1. Here we have the exponential form, x is equal to a raised to f of x. And this implies that x is greater than 0. The following are equivalent. So we have 5 cubed is equal to 125. It is equivalent. The logarithm of 125 to the base 5 is equal to 3. So it just simply means that 5 here, the subscript, the base, needs to be raised to 3 for us to obtain 125. Number 2, 2 raised to 4 is equal to 16 is equivalent to the logarithm of 16 to the base 2 is equal to 4. And then next, we have 3 raised to negative 2 is equal to 1/9, applying the laws of exponent. This is equivalent to the logarithm of 1/9 to the base 3 is equal to negative 2. Here are the laws of exponent and the laws of the logarithm. So we can use this in getting the derivative, in simplifying our answers, or simplifying the given first. Okay, we have here a raised to 0 is equal to positive 1. Take note that A and B here is a positive number, positive real number. And then M and N are real numbers. When we say real numbers, it may assume any value provided that it is real. So it includes negative numbers, zero, and positive numbers. Okay, we have A raised to 1 is equal to A. Number 2, A raised to M times A raised to N. Anong ginagawa natin? We add the exponent. For example, X times X squared. We add the exponent, X cubed. It becomes X cubed. And then it also applies for binomials. Let's say X minus 1 raised to 3. And then times X minus 1 squared quantity. Since these are the same, so we can add their exponents. So we have X minus 1 quantity raised to 5, 3 plus 2. Number 3, A raised to M divided by A raised to N, we subtract their exponents. Number 4, the quantity A raised to M raised to N. Here we have a power of a power. What we do here is we multiply the exponents. For example, we have here X raised to 10, and then quantity square. So we have here X raised to 20. Number 5, we have here the quantity AB raised to M. We distribute the exponent. And then number 6, we also distribute the exponent for quotients. And then number 7, we have here the law for negative exponents. A raised to negative M is equal to 1 over A raised to M. Conversely, this is equivalent to 1 over or A raised to M. This is equal to A raised to negative M. Okay. Example, let's have 2 raised to negative 2. This is equal to 1 over 2 raised to 2, which in turn is equal to 1/4. Next, we have the laws of logarithm. Take note that the number 1 in the law of exponent is the equivalent for the laws of logarithm. We have the logarithm of 1 to the base A is equal to 0 since A raised to 0 is equal to 1. And then the logarithm of A to the same number A is equal to positive 1. Number 2, the logarithm of a product. This is analogous to the number 2 of the laws of exponents. As you can see, we have the logarithm of M times N to the base A. We can split it into logarithm of M to the base A plus logarithm of N to the base A. So, eto yun. Number 3, logarithm of a quotient, provided that N is greater than 0, positive. The logarithm of that is equivalent to, we have here logarithm of M minus logarithm of N, both to the same base A. Number 4, logarithm of a power, we have logarithm of M raised to C to the base A. We can take down the power, put it in the front like this one. So this is analogous to number 4. And then number 5, we have a logarithm of 1 over M to the base A. This is equal to negative logarithm of M to the base A. So this one corresponds to the number 7 in the laws of exponent. And finally, we have here the logarithm of M to the base A. Using the change of base, we can actually introduce another base, B. Okay? So this will become equal to logarithm of M to the base B over logarithm of A to the base B. Let us give an example for each. For number 2, let's have here logarithm of 8. Logarithm of 8 to the base 10. Okay. This is equal to logarithm of 4 plus logarithm of 2. Why? 4 times 2 is equal to 8. Okay, number 3. How about logarithm of positive 2? So, since we are using specific examples here, take note, maraming pwedeng maging example. Since maraming numbers na pwedeng mag-come up na ganitong quotient. Okay, isip tayo ng dalawang numbers na kapag pinag-divide mo, 2 yung lalabas. So, let's have here logarithm of 16 minus logarithm of 8 because 16 divided by 8 is equal to 2. Next, let's say we have here logarithm of 4 to the base 2. So this is equal to logarithm of 2 squared to the base 2. So we can bring down this. So we have 2 times logarithm of 2 to the base 2. Or in turn, this is equal to 2 times 1, positive 2. Number 5. Okay, let's have logarithm of 1 over 16. The logarithm of 1 over 16 is equal to logarithm of 16 raised to negative 1. Okay, so using the power law, we have negative logarithm of 60. And then number 6, we have the change of base. Here, you may choose any b that you want. Suppose that the original given is logarithm of 7 to the base 2. This is equal to logarithm of 7 over logarithm of 2. Take note that here the subscript is invisible 10. And then after that, this is also equal to any base actually, provided that you follow this. This is equal to logarithm of 5 to equal to logarithm of 7 to the base 5 over logarithm of 2 to the base 5. Oh, this is also equal to, let's say, logarithm of 7 to the base logarithm of 7 to the base e, and then over logarithm of 2 to the base e, and so on. So there's an infinite equivalent expressions for this. Here are the systems of logarithm. Consider the function f of x is equal to logarithm of x to the base a. We have the following systems. Number 1, the common or the Bayesian logarithm. Here we have the common log when a is equal to 10. Okay, f of x is equal to logarithm of x to the base 10. We can actually omit the writing of 10. So when we see log only, log of x, it means that it is to the base 10. So, what is the value of log of 10? If we have an invisible 10 here. Positive 1. How about the logarithm of 100? So we have positive 2. And then also when working backwards, logarithm of 0.1. So this is equal to logarithm of 1 over 10, which is equal to logarithm of 10 raised to negative 1. So we have negative 1 log of 10. We have negative 1. Next, we have the natural or the Naperian logarithm. Here we introduce the e, the Euler's number or the natural base. When a is equal to e, then we have here the logarithm of x to the base e, or symbolically, this is written as the ln. You will see that on your calculator, and we call that the natural logarithm of x, or ln. Take note that e here is what we call the Euler's number, and it can be expressed using the limit. Here we have e is equal to the limit of the quantity 1 plus x raised to 1 over x as x approaches 0. and it is an irrational number. And aside from that, it is non-terminating, hindi natatapos. Ito yung mga first 6 digits ng ating E. Aside from that, it can also be represented alternatively by, we have here the limit of the quantity 1 plus 1 over x all raised to x as x approaches infinity. So this is also equal to E. Let us solve some problems in limits. Evaluate the limit. The limit of the quantity 1 minus e raised to x all over 1 plus e raised to x. So here we may try direct substitution. So ito try lang natin, no? Evaluate na agad natin. We have 1 minus e raised to 0 all over 1 plus e raised to 0. Take note from the laws of exponent, a raised to 0 is equal to positive 1, where a is a real number and a is not equal to 0. So take note that this law may also work on negative numbers and also on positive 1. Okay, so what will be the value? E is a number, a real number. So we have 1 minus 1 all over 1 plus 1. So we have 0 divided by 2. It exists. So we have here 0. It exists. So this is the final answer. Number 2, the limit of the quantity 1 minus e raised to x all over 1 plus e raised to x as x approaches positive infinity. So take note that we are not going to substitute infinity to the x here because that would be infinity. The limit of e raised to x as x approaches infinity is equal to infinity. And there will be no sense if we will have here 1 minus infinity all over 1 plus infinity. Walang sense. So this would become infinity over infinity, an indeterminate form. So ngayon, yung gagawin natin, hanap tayo ng paraan in evaluating this. So remember from the previous discussion, when we discuss limits, just look on the video courseware if you want to, on this playlist, the limit of 1 over x as x approaches infinity is equal to 0. This is actually can work if x is as is or we have a power. Okay. Ngayon, pwede natin gawin yan sa exponential function na ito. What are we going to do? So, kailangan natin mapalabas ito. Sige. So, we can divide e raised to x over e raised to x to the entire fraction. So, this becomes the limit of 1 over e raised to x minus 1. Okay. We will divide all the terms. And then 1 over e raised to x plus 1. Okay. And then we distribute the limit operator to all of this. Take note that the limit of 1 over e raised to x as x approaches infinity. So, eto na yung pwedeng maging equal sa 0. Just like earlier, we have 1 over x raised to n. As x approaches infinity, this also becomes 0. Take note that when we have a denominator that is going to be very, very, very large, it will approach 0. 1 over e raised to x will approach 0 as the limit. Okay, now, we have here 0 minus 1 all over 0 plus 1. We have negative 1 as the limit. If you want to verify the answer, you may look up the graph of 1 minus e raised to x all over 1 plus e raised to x. So that you can see that it is approaching negative 1 as x approaches infinity. Number 3, we have here the limit of the ln of the quantity 4x squared minus 2x plus 2 all over 7x minus 2x squared as x approaches positive infinity. So take note that here, yung mag-approach ng infinity is yung x, nasa loob ng ln. So, we can insert the limit operator inside the ln. So we have 4x squared minus 2x plus 2 all over 7x minus 2x squared. So recall from limits at infinity, kapag meron tayong ganyan, titignan natin yung highest powered variable sa numerator and denominator. Okay, we have here 4x squared and then over negative 2x squared. So actually, kahit ito na lang yung tignan natin, pag pinag-divide natin to, it becomes negative 2. Isn't it? Here we have the ln of negative 2. So this one does not exist because negative numbers have no logarithms. Meaning to say there's no exponent that would come up with negative 2 when we raise e to it. So x, there is no value of x such that when e is raised to it, the result would be negative 2. You have reached the end of this part. You may proceed to the differentiation of logarithmic function.